Hello students, welcome to online classes. So we are discussing class 12 mathematics chapter 1. So in our last video we have studied what do you mean by relations and types of relations. Okay, we have seen some examples also. Now today in this video we will try to solve some problems. Okay, these problems are from your previous year's question paper. Okay, and some problems are from your textbook. Okay, so if you go through these problems, then you will understand the concept better way. Okay, and another thing also, first you see the question. Okay, first you see the question and try to solve yourself. Okay, then after that you see my explanation. Okay, so let us start. We have studied equivalence relation. Equivalence relation means what? A relation is said to be equivalence if it is reflexive, symmetric and transitive. Reflexive we know A comma A belongs to R for all, every A belongs to the set. Okay, and your symmetric is if A comma B belongs to R, then B comma A belongs to R. Okay, and your transitive relation, if A comma B and B comma C belongs to the relation, then A comma C must be belong to the relation. Okay, then we can say this type of relation is transitive. Okay, so first question, what it says, let us check whether the relation R equal to x comma y such that 3x minus y equal to 0 defined on the set A equal to 1, 2, 3 up to 14 is an equivalence relation or not. Okay, so for showing if a relation is an equivalence relation or not, what we have to show, what we need to check, three properties we need to check. First property is your reflexive property. Okay, reflexive property. Second is your symmetry, and last is your transitive property. Okay, so if this type of relation is given in terms of x and y, it is defined, and the set is a finite set, then we try to find all the ordered pairs. Okay, so let us try to find out. R contain, you can say x comma y such that 3x minus y equal to 0. So this can be written as x comma y such that we can say y equal to 3x. Now what are the elements will come? If I put x is equal to 1, then what is the value of y? 3. And if I put x is equal to 1, if I put x is equal to 2, then what is the value of y? 6. And if I put x is equal to 3, then what is the value of y? 6 is a 9. And if I put x is equal to 4, then what is the value of y? 3 4 is a 12. Okay, then another thing, if I put x is equal to 5, then next it will be 4 comma 5. So if I put x is equal to 5, then 3 5 is a 15, but 15 does not belong to the set. Here both x comma y belongs to the set A. Why? Because this set is defined in the set 1. Okay, so this is our order. Okay, so this is our relation. Now for reflexive property, first one. So if in your question it is asked there, show that check whether the relation is an equivalence relation or not. What we know, for equivalence relation, three property must satisfy. Okay, but if one of the property does not hold in that relation, then it is straightforward to reject that it is not an equivalence relation. Okay, so and for when you write the solution, you show one of the property does not hold, then it is okay. Okay, now I am showing these three properties. So first property is reflexive property. We know for reflexive property, A comma A belongs to the relation for every A belongs to the given set. Okay, now set A contain 1 to up to 14 means all element must be there. 1 comma 1, 2 comma 2, then 3 comma 3, and so on up to 14 comma 14 must be there in the relation. But if one element is not there, we will directly straightforward reject this. This is not a reflexive relation. So you will write since 1 comma 1 does not belongs to the relation Therefore, R is not reflexive. Not reflexive, showing not reflective is easy. You try to find one element in A whose doublet is not there in the relation, then it is automatically not reflexive. Okay, but when you want to prove a relation is reflexive, you have to show for all elements. Mean what are the elements in A? এর মধ্যে যতটি এলিমেন্টস থাকবে তার প্রত্যেকটি ডাবলেটটা শো করতে লাগবে যেটা আর এর মধ্যে আছে। ঠিক আছে? সো নেক্সট কোশ্চেন, next property, that is your symmetric property. Symmetric property. Okay, symmetric relation. Okay, so for symmetric relation we know A comma B. If A comma B belongs to the relation, then its ulta means its reverse must be also belongs to the relation. Imply that. Okay, so check whether 1 comma 3 is there, its ulta means 3 comma 1 must be there. 3 comma 1 is not there, so we'll directly still write since 1 comma 3 belongs to the relation but 3 comma 1 does not belong to the relation. Therefore, R is not symmetric. Okay, so next, whether this relation is transitive or not, let us check. Transitive relation or not. So see, 1 comma 3 means A comma is B is there, so 3 comma something B comma C, we have got this B comma C. Okay, so A comma C, whether we have to check whether A comma C is there. A comma C means 1 comma 9 is there, no, so this is not a transitive. So we'll write since 1 comma 3 and 3 comma 9, this is our AB and this is our BC belongs to the relation, but 1 comma 9 does not belongs to the relation. Therefore, R is not transitive. Check whether R equal to relation is given A comma B such that A comma B belongs to Z and A less than B is an equivalence relation or not. We have to check. So our two solution. First is whether this relation is reflexive or not. Okay, so let us check. So for reflexive, for every A belongs to Z means for every integer we have to show A comma A belongs to R. For A comma A belongs to R, it should be A less than B. So you check, we know 1 belongs to Z, but 1 does not less than 1. If it is 1 less or equal to 1, then it's okay, we can say, but strictly it does not less. Okay, for any number, can I say 2 is less than 2? No, it's not possible. 2 is less or equal to 2, we can say. Okay, so but 1 does not less or equal to 1, therefore we can say 1 comma 1 does not belongs to the relation. So if one of the element is not there, then this is not reflexive. So therefore R is not reflexive. Okay, number 2 is our symmetric relation, whether this relation is symmetric or not, we have to check. Okay, symmetric, we have 1 comma 2 belongs to the relation as 1 is less than 2. Okay, but if symmetric relation, but if 1 2 is there, then we have to show that 2 comma 1 is also there, but 2 is does not less than 1. Is 2 is less than 1? No, so therefore 2 comma 1 does not belongs to the relation. Therefore R is not symmetric. Okay, next, transitive and B comma C belongs to the relation. Therefore we can say A is less than B and B is less than C. So we can take examples also. We know 1 is less than 2 and 2 is less than 3. Therefore we can say 1 is less than 3. It is obvious. Okay, so for every integer it holds. Therefore we can say from these two lines we can say A less than C. If A less than C, this implies you can say ordered pair A comma C belongs to the relation. Okay, so therefore R is transitive. Okay,
Therefore R is not an equivalence relation.
Next question, question number 3. Let's see. Give examples of two relations such that one is equivalence relation and the other is not. Okay. So we have to give two examples on a set which one is equivalence relation and the other is not. Okay. So first we have to consider a set, because set is not mentioned. We know relation is defined in a set. Suppose a equal to 1, 2, 3. Now R1 I am defining. Okay. Suppose first example, two relations such that one is equivalence relation. For equivalence relation, what are the properties satisfied? That relation should be reflexive, symmetric and transitive. Okay. So first I am considering this set. So what we have defined, R1, 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Okay. Next, let us try to define R2. R2 says which is and the other is not a transitive, and other is not an equivalence relation. So R2 I am defining, suppose 1, 1, 3, 3, 1, 2 and 2, 1. Okay. So let us check whether R1 is, these are the two examples we are considering. Okay. Now whether check this is an equivalence relation or not. R1, is it an equivalence relation? For equivalence relation we have to check reflexive, symmetric and transitive. For reflexive property, for every A belongs to the set. ঠিক আছে, এর প্রত্যেকটি এলিমেন্টের ডাবলেট আছে কি নাই? আছে। ঠিক আছে, তারপরে কি চেক করতে লাগবে আমাদের? ট্রানজিটিভ সিমেট্রিক প্রপার্টি। সিমেট্রিক প্রপার্টি মিন্স হোয়াট? যে সমস্ত অর্ডার পেয়ার থাকবে তার উল্টাটা থাকতে লাগবে, মানে 1,1 উল্টাটা 1,1, 2,2, 3,3, every pair is there. 1,2 2 and 2,1, 1,2 তার উল্টাটা হবে 2,1, 2,1 এর উল্টাটা হবে 1,2 is there. So this is a which type of relation? This is also symmetric relation. Okay, now next is transitive. Transitive property 1,1, 1, something is there. 1,2 is there. 1,1 is there. So B element. This is our AB. This is our AB. So BC. So this is our BC. Now whether AC is there, AC, what is the element? A, C. A, C means 1,2. This is the element. Okay, next 2,2. Okay, 2,2 is there, means this is our AB. Then next we have to find out BC. Okay, this is our BC. AB and BC. 2,1 AB and 2,2 AB and 2,1 is our BC. Then AC must be there. AC, what is the element? AC. AC means 2,1. Yes, this is the element there. And next 3,3 is there. So we have got 3 as our B. So 3, something is not there, no need to check. Next is 1,2. 1, something is there. 1,2 and 1,1. This is our 1,2 A, B. And next should be B,1, B, C. So this is our B, C. Okay. Then now whether AC is there or not. AC means 1,1. Yes, it is there. We have seen R1 is reflexive, symmetric and transitive. So it is an equivalence relation. This is the example. Okay. Next R2. Whether this is an equivalence relation or not. For equivalence relation, what we have to check? Is it reflexive, symmetric or transitive? One of the property left, then it will not be equivalence relation. It's 1, 2, 3. So doublet must be there, doublet elements. So 1,1 is there, 2,2, 2,2 is not there. So this is not reflexive. Not reflexive means not an equivalence relation. Okay, one property does not hold, then this is not an equivalence relation. Okay, so let's see next question. Question number 4 solution. What the question says, give an example of a relation which is symmetric and reflexive but not transitive. So suppose a set is, we are considering the set 1, 2, 3. R is a relation I am defining. What is the relation? 1,1, 2,2, 3,3. Why I have taken these 3 elements? Because the question says it must be reflexive. So it is reflexive. Next is what it says. Symmetric. So for these elements, no problem. So if I take only these elements, then this will be an equivalence relation. This is also transitive. Okay. So we have to take other elements also. Suppose if I take 1,3 and 3,1. Okay. So 1 comma 3 and 3 comma 1 is there, those, so it is symmetric also. Okay. Now if I don't take other elements, then it will also transitive, because a comma b and b comma c is there and a comma c is there, 1 comma 1 is there, element is there already. Okay, so I have to take more elements. So if I take 2 comma 3 and 3 comma 2, so ab is there, bc is there, ab and bc is there. Okay, so 2 comma 2 is there. Now if I take ab is, and this is our bc, then what will be our AC? AC will be 2 and 1, 2 comma 1. But 2 comma 1 is not there in the relation. So this is not a which type of relation? This is not a transitive relation. Okay. So you will write that this relation is reflexive. Why? Because 1 comma 1, 2 comma 2, 3 comma 3 R belongs to R. This is symmetric also, because every element has its figures. And it is not transitive. Why? It is not transitive. Why? As we'll say, the R is not transitive as. Why? With AB we are taking 2 comma 3 and BC 3 comma 1 belongs to the relation, but AC means 2 comma 1. 2 comma 1 does not belong to the relation. Okay. Okay. So see question number 5. Question number 5, what it says? Let A equal to 1 to 3. For x comma y belongs to A, let x is related to y if and only if x is greater than y. Write down R as a subset of across A. So here set is not defined in set beta form. We try to define. Suppose let R equal to, our relation is not divided in set beta form. We try to define. It says it contains the ordered pairs such that x comma y both belongs from A and x is related to y if, how the relation is defined, x is greater than y. Okay, so this is the relation of defined. Okay, A contain only 3 number of elements, so we can easily find out A across A. So easily we can find out. So 1 comma 1, then 1 comma 2, then 1 comma 3. Then next will be 2 comma 1, then 2 comma 2, and 2 comma 3. Then next will be 3 comma 1, 3 comma 2, and 3 comma 3. Now you pick up the elements. First element is our x and second element is y. First element is our x and second element is our y. Okay. First element is our x and second element is our y. So we have to pick up the elements such that x is greater than y. So therefore R will be, what are the elements? 1 will not be there. 1 is greater than 2, no. 1 is greater than 3, no. 2 is greater than 1, yes. So 2 is greater than 1. 2 is greater than 2, no. 2 is greater than 3, no. 3 is greater than 1, yes. 3 will be there. 3 is greater than 2, yes. Is 3 comma 3 is there? No. So R is the subset of. Question number 6. Let L be the set of straight lines in xy plane and R is a relation on L defined as R is equal to set of ordered pairs L comma L1 comma L2 such that L1 is parallel to L2. Show that R is an equivalence relation. Find all the lines related to y equal to 2x plus 4. So how to show any relation is an equivalence relation? First we have to check reflexive property. Reflexive. Is this relation is a reflexive relation? We know if any line is given, it is parallel to itself. So we can say for any L1 belongs to the capital L, L1 is parallel to L1. Therefore L1 comma L1 belongs to the relation. For any L1 belongs to L. Okay, means for all L1 belongs to the. Okay, next number 2 property is our symmetric property. Okay, so symmetric property, let L1 comma L2 belongs to the relation. Therefore we can say L1 is parallel to L2. This is the way the relation is defined. Okay, so if one line is, this is L1 and this is L2, if L1 is parallel to L2, then we can say L2 is parallel to L1. So this is, therefore we can say L2 is also parallel to L1. Therefore if L2 is parallel to L1, then L2 comma L1 belongs to the relation. Therefore R is what? Symmetric. Okay, next third property, this is transitive or not. Let us check. So let L1 comma L2 belongs to the L1 comma L2. Let L1 comma L2 and L2 comma L3 belongs to the relation. Okay. If L1 comma L2 belongs to the relation, therefore L1 is parallel to L2, and L2 comma L3 belongs to the relation. That means L2 is parallel to L3. Okay. So if L1 is parallel to L2 and L2 is parallel to L3, L1 and L2 is there. So L3 is there. We know L1 is parallel to L2, L2 is parallel to L3. Now can I say L1 is parallel to L3? Yes, obvious. From this you can say L1 is parallel to L3. This implies L1 comma L3 belongs to the relation. Okay. Therefore what we have got? Therefore R is transitive. Okay. So what we can say now? Therefore R being reflexive, symmetric and transitive, therefore and so R is an equivalence relation. Okay. So let us try to find out now next part. The next part of the question says that you have to find out all the lines which is related to y equal to 2x plus 4. Now if I take let L1 is any line, okay, which is parallel to the line y equal to 2x plus 4. We need to find out the lines which are related to L1. Meaning is that the lines which are parallel to y equal to 2x plus 4. Now we know if two lines are parallel, then their slopes are same. Only they are differ by constant. Okay. So we can say therefore the lines parallel to y equal to 2x plus 4 will be what? Y equal to 2x plus c, where c belongs to any real number. Okay, Jacono real number, this is true. Okay, therefore the set of lines will be, what are the set of lines? Lines are which are related to y equal to 2x plus 4 is y equal to 2x plus c such that c belongs to any